This video builds off the last video that we just watched that was sort of a qualitative description of heat capacity. Well, it was quantitative too, but now we're going to work with some of those equations that were pictured in the last video. So we want to talk some about heat capacity. Alright, so imagine that I have here a block of some material and there's some fire underneath it. So as diagrammed here, we see that heat is going to go from the fire into the block. So what's going to happen? Well, as you heat the block up, of course it's going to get warm, so its temperature is going to increase. So the more heat we put in, the higher the temperature. And so what we can say is that the amount of heat then is going to be somehow proportional to the temperature change, delta T. Right? So I'm going to write delta T there. So the heat then, and this is my symbol right here for proportional to, is proportional to the temperature change. And remember, delta T is going to be T final, T sub F, minus T sub I, because our delta symbol always means final minus initial. So if we know how much the temperature has gone up, that's going to be proportional to the amount of heat. So in order to turn this proportionality into an equality, what I need is a proportionality constant. And that proportionality constant is called the heat capacity. So it's given a capital C with a subscript capital P. So that heat capacity times delta T. So this is really useful. It tells us if we can measure the temperature change and we know the heat capacity, we can calculate the amount of heat. Or in fact, if we know any two of these three variables, or even one of these T finals and T initials, we can solve for the variable that we don't know. We just have to know all of the other variables except one. So this quantity right here again, C sub P, is called the heat capacity. And we have an understanding of what that means from the previous video. So that's heat capacity. Heat capacity is going to have units of joules per degree Celsius or joules per degree Kelvin. You can do that because the Kelvin degree and the Celsius degree are the same size. So joules per Kelvin or joules per degree Celsius. So let's imagine that we have a different experiment here. So now we've got a much bigger block. So here's a bigger block of that same material. And we've still got our fire, but now it looks kind of punier underneath here. And there's still heat that's going into our system, our block. So what's going to be different this time? Well, if I put in the same amount of heat, the temperature of our block is going to go up by a lot less. Why? Because it's got a bigger block, right? So that block can hold less heat for given temperature rise. So if you take a heater and you try and heat up a test tube full of water or a swimming pool full of water, put the same amount of heat into both, the temperature changes are going to be very different, right? And that's because those two substances have different heat capacities. So even though it's the same material, the bigger block has a bigger heat capacity, right? So C sub P for the block, the big block, is going to be much greater than the C sub P for the small block. Oh, by the way, this P that is right here, that does have special meaning. So C for heat capacity, the C for capacity, but the P stands for constant pressure. So it turns out that heat capacity changes, the numerical value changes a little bit depending on the conditions of the measurement. So if you're doing your measurement under conditions of constant pressure or constant volume, you might get somewhat different numbers but depending on the substance. So the CP here is reminding us that this is a constant pressure process. By the way, the technical scientific term for a constant pressure process is isobaric or isobaric. So iso means same and bar for pressure. So constant pressure process, isobaric. So that's what this CP means. And again, CP then depends on the amount of material that you have. So let's scroll down here a little bit, give us some more space. So CP is what we call an extensive property. So we know what extensive means. It means it depends on the amount of material. So we've seen in the past that we can create an intensive property which doesn't depend on how much stuff you have and would just be a property of the material by taking two extensive properties and dividing them. So what we're going to do now is we're going to divide CP by the amount of stuff that we have. Now there are different ways that we can measure the amount of stuff in this block. We can either count the molecules in moles, or we can divide by the number of grams. So if we divide by the number of grams of substance, then we get a new quantity that's called lowercase. Your book uses this notation. It's a lowercase c with a little subscript s. The S stands for specific, because it's specific for 1 gram of substance. So it's the heat capacity per 1 gram of substance. If we divide the heat capacity by the number of grams of that substance, we'll get the specific heat capacity. And so specific heat capacity has units of joules per gram degree Celsius or degree Kelvin, either way. And so what it is, it's the energy delivered as heat to raise the temperature of 1 gram of substance by 1 degree Celsius at constant pressure. So that's what we mean by specific heat capacity. So it's how much heat energy you have to put in to raise the temperature 1 degree Celsius of 1 gram of that material. So so this is an intensive property of material now, because we've divided 2 properties that are extensive. Heat capacity is extensive and mass is extensive. We can create another heat capacity, and this one is given a lowercase c sub p, and it's just capital C sub p divided by the number of moles of substance that we have. And so this will have units of joules per mole per degree Celsius. And so this is called the molar heat capacity, and it's just the energy required to heat 1 mole of substance by 1 degree Celsius. Okay? So 2 different intensive heat capacities: the specific heat capacity, the top one, C sub S, and the molar heat capacity, lowercase c sub p. So these are both lowercase c's, and these c's here capital C's for the heat capacity. So these are both intensive properties. These are properties of materials, just like their densities, their melting points, their boiling points. And so we can sometimes use these to identify or characterize different materials. But now what we're going to do is use these in calculations. But before I go away from this, I wanted to point out that we can convert between specific heat capacities and molar heat capacities really easily. So if we just think about their units, here we have Cp divided by the number of grams of substance. So if I wanted this to be Cp divided by the number of moles of substance, all I would need to do is multiply by molar mass, right? So if I have Cp, I'm just going to have units of joules per degree Celsius, and that's divided by the number of grams of substance. And if I come in and multiply by molar mass, I will know the number of grams per mole of that substance. The gram unit would cancel out, and then I'll be left with something that has units of joules per degree Celsius per mole, and that's just the molar heat capacity. So let me write down that in an equation. So the molar heat capacity, Cp, is equal to the specific heat capacity, Cs, times, little dot there, the molar mass. So you can just look up the molar mass of your substance, multiply it by the specific heat capacity, and find the molar heat capacity. Or if you need to find the specific heat capacity from the molar heat capacity, you just divide by the molar mass. So that's real easy to do. So let's use these numbers in some calculations. So the equations that we get then allow us, and we saw those in the last video, the amount of heat then is equal to the heat capacity times delta T, or if we're talking about specific heat capacity, it's going to be the mass times the specific heat capacity times delta T. So one of my former students said this kind of looks like, since the delta looks a little bit like a capital A, some people call this the Mcat equation, right? MC delta T looks kind of like Mcat. So those of you that are pre-med students know about the Mcat, because it's this big high-stakes exam that's looming in your future. Okay, so this is a way that we could calculate the amount of heat involved when an object, a substance, changes its temperature if we know its heat capacity. So M is going to be the mass then. There's another formula that looks a lot like it that we can use to calculate also the heat, and that's if we know the number of moles of substance N. So we're going to let N be our symbol for number of moles of substance. We're going to multiply that by the molar heat capacity, little c sub p, times delta T. So either of these 2 equations will let you relate a heat to a temperature change. So let's just do a quick calculation to see how that works. So I'm going to leave those 2 equations up here so we can scroll down a little bit. And here's our problem. How much energy as heat is required to warm water from 18 degrees Celsius, that's cold water, to 35 degrees Celsius, which is nice hot water, for a bath? Okay, so we want to write the question down. So again, here's our question: how much energy to heat water from 18 degrees Celsius to 35 degrees Celsius for a nice hot bath? So before we can solve this problem, we need to know some more information. First off, we need to know a heat capacity information for water. So it turns out that the specific heat capacity for water, so I'll put a little subscript H2O so I know that's the material that I'm talking about, is 4.184 joules per gram per degree Celsius. So I need that information. And I also need to know, since I'm going to fill up a bathtub with hot water, I need to know the typical volume of a bathtub. And so looking that up online, it turns out that typical bathtubs maybe have a volume of about 270 liters. So that's how much hot water you would need to fill up your bathtub. And another feature that I know about water is its density. So density of water is equal to 1 gram per milliliter. Or equivalently, I've got 1 kilogram per every 1 liter. Okay, so those are the same. So this tells me then, looking at this density, that I've got about 270 kilograms of water in my bathtub. Okay, so now I can set up my equation to calculate this. So Q is equal to M times CS times delta T. So I know all of these pieces of information, so I can calculate the amount of heat. So mass, so I need that in grams because my specific heat capacity is in grams. So that's going to be 270 times 10 to the third grams of water. And I multiply that by the specific heat capacity of water, 4.184 joules per gram per degree Celsius. And then I need to multiply that by the temperature change. So my final temperature is going to be 35 degrees Celsius minus my initial temperature, which is 18 degrees Celsius. And so that gives me a temperature difference of 17 degrees Celsius. And we see that the degrees C will cancel out here, and that the grams will cancel out here, leaving my only answer as joules. So I punch that into my calculator, and I get as a final answer that this is 1.92, not 7, 1.92 times 10 to the 7th joules. That's equivalent to 1.92 times 10 to the 4th kilojoules, or 19,200 kilojoules. So you may be more familiar, those of you in the US, with the English system for measuring heat energy. So for heating homes or hot water heaters, we might use something called the British Thermal Unit, which stands for, the acronym would be BTU. So this is also equivalent to, we could do the conversion there, about 18,200, oops, that's supposed to be a comma there, 200 British thermal units, BTUs. There we go. So a typical hot water heater for a house might have a heating capacity of somewhere between 32,000 and 40,000 BTUs per hour. So that'll tell you how many bathtubs full of water you could heat per hour with your particular hot water heater. So there's a very useful calculation. We've calculated how much heat energy would be required to heat water up.